Hello everyone, my name is K. Rajesh. I am from CSC B section. Today's my topic is about comparison of time and space complexity. Introduction. Every day we come across many problems and we find one or more than one solutions that particular problem. Some solutions may be efficient as compared to others and some solutions may be less efficient. Generally, we tend to use the most efficient solutions. For example, while going from your home to your office or school or college, there can be n number of paths, but you choose only one path to your destination, the shortest path. The same idea we apply in the case of the computational problems or problem solving via computer. We have one computational problem and we can design various solutions, that is algorithms, and we choose the most efficient algorithm out of those developed algorithms. Algorithm in computer science, whenever we want to solve some computational problems, then we define a set of steps that need to be followed to solve that problem. These steps are collectively known as an algorithm. For example, you have two integers a and b, and you want to find the sum of those numbers. How will you solve this? One problem solution for the above problem can be: take two integers as input, create a variable sum to store the sum of two integers, put the sum of those two variables in the sum variables, return the sum variables. The code is as given below. In the above example, we will find three things, that is input, algorithm, and output. Input. Input is something for which you need to write an algorithm and transform it into a desired output. Just just like in machines, where you give some raw products and machine transforms to the raw products into some desirable products. In our example, the input is of two numbers, that is a and b. Before writing an algorithm, you need to find the data type of input, distribution or range of input, and other relevant details related to it. So, critically analyze your input before writing the solution. Algorithm. An algorithm is well defined steps by step procedure that takes some value or set of values as input and produce some values or set of values as output. In the above example, we are having these three steps to find the sum of two numbers. So all three steps are collectively called as an algorithm to find the sum of two numbers. Output is desired result in the problem. For example, if we are finding the sum of two integers a and b, then for every value of a and b, it must be produce the correct sum of the sum as an output. Good algorithm. These can be many algorithms for a particular problem. So how will you classify an algorithm to find good and others to be bad? Let's understand the properties of a good algorithm. Correctness. An algorithm is said to be correct if for every set of inputs it halts with the correct output. If you are not getting the correct output for any particular set of, then your algorithm is wrong. Fitness. Finiteness. Generally, people ignore this, but this is the one of the important factor in algorithm evolution. The algorithm must always terminate after a finite number of steps. For example, in the case of recursion and loop, your algorithm should terminate, otherwise you will end up having a stuck overflow and infinite loop scenario respectively. Efficiency. An efficient algorithm is always used. By the term efficiency, we mean to say that the algorithm should efficiently use the resources available to the system. The computational time, the time taken to generate an output corresponding to the particular input should be as less as possible. The memory used by the algorithm should also be as less as possible. Generally, there is a trade-off between computational time and memory. So we need to find it the time of more important than space or vice versa, and then write the algorithm accordingly. So we have seen the three factors that can be used to evaluate an algorithm. Out of these three factors, the most important one is the efficiency of algorithms. So let's dive deeper into the efficiency of the algorithm. Algorithm efficiency. The efficiency of an algorithm is mainly defined by two factors: space and time. The good algorithm is one that is taking less time and less space, but this is not possible all the time. There is a trade-off between time and space. If you want to reduce the time, then space might increase. Similarly, if you want to reduce the space, then the time may increase. So you have to compromise with either space or time. Let's learn more about space and time complexity of algorithms. Complexity. Space complexity of an algorithm denotes the total space used or needed by the algorithm for its working for various input sizes. For example, vector int my vector for int I is equal to 0, I less than n, I plus plus. C in is greater than my vector of I. In the above example, we are creating a vector of size n. So the space complexity of the above code is in the order of n. That is, if n will increase, the space requirement will also increase accordingly. Even when you are creating a variable, then you need some space for your algorithm to run. All the space required for the algorithm is respectively called the space complexity of an algorithm. Note: in normal programming, we will be allowed to use 256 MB of space for a particular problem. So you can't create a array of size more than 10 power 8 because you will be allowed to use only 256 MB. Also, you can't create an array of size more than 10 power 6 in the function because the maximum space allotted to the function is 4 MB. So to use an array of more size, you can create a global array. Time complexity. The time complexity is the number of operations an algorithm perform to complete its task with respect to input size. Considering that each operation takes the same amount of time, the algorithm that performs the task in the smallest number of operations is considered to the most efficient one. Input size. Input size is defined as total number of elements present in the input. For a given problem, we categorize the input size as n approximately. For example, sorting problem, total number of items to be sorted. Graph problem, total number of vertices and edges. Numerical problems, total number of bits needed to represent a number. The time taken by an algorithm also depends on the computing speed of an algorithm. By using by using but we ignore those external factors and we are only concerned on the number of times a particular statement is being executed with respect to the input size. Let's say for executing one statement, the time taken is less than what is the time taken for executing n statements. It will take n seconds. There are three asymptotic notations that are used to represent the time complexity of an algorithm. They are theta notation, big O notation, omega notation. Theta notation. The theta notation is used to find the average bound of the algorithm, that is, it defines the upper bound and the lower bound, and your algorithm will lie in between these levels. So, if a function is g of n, then the theta representation is shown as theta of g of n. Then the relation is shown as theta of g of n is equal to f of n. There exist positive constraints c1, c2, and n0, such that 0 less than or equal to c1 g of n less than or equal to f of n less than or equal to c2 g of n for all n greater than or equal to n0. The above expression can be read as theta of g of n is defined as set of all the functions f of n for which there exists some positive constraints c1, c2, and n0, such that c1 into g of n is less than or equal to f of n, and f of n is less than or equal to c2 into g of n for all n that is greater than or equal to n0. Omega notation. The omega notation denotes the lower bound of the algorithm, that is, it takes taken by the algorithm can't be lower than this. In other words, this is the fastest time in which the algorithm will return as a result. It's the time taken by the algorithm when provided with the best case input. So if the function is g of n, then the omega representation is shown as omega of g of n, and the relation is shown as omega of g of n is equal to f of n. There exist positive constraints c and n naught, such that 0 less than or equal to c g of n less than or equal to f of n for all n greater than or equal to n naught. The above expression can be read as omega or g of n is defined as a set of all the functions f of n for which there exist some constraints c and n naught, such that c into g of n is less than or equal to f of n for all n greater than or equal to n naught. Big O notation. The big O notation defines the upper bound of the any algorithm, that is, your your algorithm can't take more than this time. In other words, we can't say that the big O notation denotes the maximum time taken by the algorithm or the worst case time complexity of an algorithm. So big O notation is the most used notation for the time complexity of an algorithm. So if the function is g of n, then the big O representation of g of n is shown as big O of g of n, and the relation is shown as big O of g of n is equal to f of n. There exist positive constraints c and n naught, such that 0 less than or equal to f of n less than or equal to c g of n for all n greater than or equal to n naught. The above expression can be read as big O, big O of g of n is defined as the set of functions f of n for which there exist some constraints c and n naught, such that f of n is greater than or equal to 0, and f of n is smaller than or equal to c into g of n for all n greater than or equal to n naught. Conclusion. Both time and space complexity are two important parameters for evaluating a solution. Ne- Nevertheless, with the current evolution in hardware technology, space complexity is no longer essential because almost all machines have enough memory. However, the time complexity is still a crucial way to evaluate algorithms. Thank you.